Hello and welcome to my final project for machine learning, which is to predict traffic volume. My name is Ben Hoffman. The data that I used, I got from the UCI machine learning repository. As you can see, it contains hourly traffic volume between Minneapolis and St. Paul on westbound I-94. Quick look at the attributes here. You can see it has holidays, temperature in Kelvin, rain and snowfall by the hour, percentage of clouds, weather categories, and here we have a date time feature where you have the year, month, day of the month, and the hour all contained in one, which I had to separate. Also, there's the traffic volume itself. Exploring the data, I used histograms with all of the numeric attributes. Also did some linear model. As you can see here, for example, the temperature has some erroneous records storing at absolute zero. So I had to get rid of those as outliers and impute values. Here you can see where I extracted the year, month, day of the week, and hour of the day from the date time field. Then created dummy columns for each one of them for the year, month, day, week, hour of the day. Also the weather categories and holidays, which the holidays I just turned into a binary field, whether it was either holiday, yes or no. Also looked at average volume by the day of the week and by hour of the day, just to make sure that it made sense. Did yearly and monthly as well. For the algorithms, I used multiple linear regression, neural networks, and support vector machines. Because of the nature of these second two algorithms, I did normalize all of the data. Here you can see the linear model that I used for regression. This is after backfitting. Even after backfitting, I still had about 49 attributes that I'm testing. You can see here, this is after all the p-values are less than 0.05. So some of the months, some of the days, many of the weather attributes were removed. Going down to creating the data frame, running the prediction. Here's the neural networks. I actually had to reduce the size of the training data for neural networks and support vector machines down to 10,000 from 24,000, which is what I used for regression, but it didn't complete in less than an hour. So I just ran it with 10,000 records instead. The results were still pretty good. I used one hidden node and then with 3 hidden nodes. I tried it with 5, but even then after running for 90 minutes it wouldn't complete, so I eliminated that from the test for this one. Support vector machines here also ran with 10,000 records using 4 different kernels, the vanilla, RBF, Poly, and Laplace. I created 4 ensemble models using an average. I just experimented with various weights. What I did is I found the mean absolute deviation for the models that I'd already used, picked the top 4, or the ones that had the least error, and just try different ones. The neural network model with 3 hidden nodes is the one that had the best, so I gave that a weight of 4. Support vector machines with the RBF kernel with a weight of 3, Laplace, and neural network also with a weight of 1. These are the ones I just experimented with different weights. It turned out this one was the best performer of the ensemble models. To evaluate the models, I used mean absolute deviation, also mean squared error, and root mean squared error. Right here, you can see I created absolute deviation for each one of the models: regression, neural network, support vector machines, and here's Laplace, for example. There's mean absolute deviation for regression was 586 cars, compared to, say, neural network with 3 hidden nodes was 288. So basically twice as good, or half the error. Did the same thing with mean squared error here and root mean squared error. Also did confidence interval for the regression predictions, and had a little plot point here of the actual traffic volume and the confidence interval that it falls within. That's at 95% confidence. Put all of the mean absolute deviation scores into one bar plot just so you can see them visually, and so I could see them visually. The neural network had the smallest error when using 3 hidden nodes. Perhaps it would have been better using 5 hidden nodes, but I just didn't have the hardware to run that. That one's right here. The support vector machine with the RBF kernel is right here. That also had a very low error. The second ensemble basically averaged this one here and that one there, and a couple of the others as well, with a very low weight. So that was a pretty good score for the ensemble model. Next, what I did is I ran the whole thing through a test data set, the separate data, using the holdout method. So my training data was 50%. Validation data was I did through the first set of tests was 25% of the records, and then this last, what's called test set for the holdout method, was used for the last 25% of the records. And as you can see, the scores are comparable as far as from the test set to the validation set. The same pattern in here. The neural network model with 3 hidden nodes had the lowest error in all of them. Like right here, the support vector machine with the poly kernel and the support vector machine with the vanilla kernel performed very poorly in all of them. Regression was okay, but not so great. This, by the way, is a mean squared error rather than the mean absolute error. I just used that for purposes of illustration because it exaggerates the differences a little bit more. It's easier to see them visually. This is just a plot of some of the data points, just the first 20 data points. They're not sequential, they're not in chronological order because they were randomized before separating the data sets, but it does give you a sense of just where the actual data points are in terms of traffic volume and where the predicted points are in terms of traffic volume. I just chose to illustrate the 3 models that had the lowest error, and as you can see, almost always the ensemble model is in between the other two. Like for example here, neural network, support vector machine, and in the middle is the ensemble. What's interesting here is on this data point that all of them are way off here. So that's an opportunity to improve the model if a pattern could be identified. Maybe they predicted poorly on weekends or during rush hour. So what did I learn? I learned that these machine learning algorithms can be very powerful. Uh, in this case, the neural network model had approximately half the absolute error as regression. Most of the data analysis I've done in the past has been using regression. It seems to be the benchmark, and the neural network model outperformed it in predicting the traffic volume in this example. I took the range by subtracting the minimum from the maximum and then divided the mean absolute deviation for these two models by the range just to illustrate it. As you can see, the error was less than half, so works really well. Also learned a lot just by going through doing the model myself and implementing the algorithms myself rather than reading it out of a book or watching someone else or listening to a recording of it. Thanks for listening.